Okay, BC, this is for you. This is to help you get ready for your first practice test for your response. These are specific. And we're just doing a crash course real quick, reviewing some of the things that we talked about for a while. And then, of course, we'll go more in depth, as things go on. Now, this problem should be graphing calculator problem. I didn't write that, but it should be. And so let's take a quick look at these just to start to jog our memory. An object move along a curve in the xy plane has position xt, yt at time t with dx dt equals cosine t cubed and dy dt equals 3 sine t squared. The first thing, so this is 2D motion. This is parametrics, right? So parametrics, 2D motion. Write an equation for the line tangent to the curve. Okay, find the speed of the object time 2. Find the total distance traveled from 0 to 1. Find the position at time 3. One of the things I might do right away is put these two equations in my Y menu. I don't think I'm mentioning graphing them, but it's going to make it easier to recall these using vars, Y vars, and not have to retype these every time. So make sure you type them correct one time. I mean, they're not too bad, but still would be nice. Okay, double, triple check them. Make sure you're in radian mode because that has trig. So just have those in there for now. At time 2, the object is at position 4, 5. So this is your initial condition. That means that x2 equals 4 and y2 equals 5. So this is x and y. All right. So it says write an equation for the tangent line to the curve at this xy point. Now, to write the equation of the tangent line, you need a point, which they give you, and a slope, which you don't have. Now, the slope of a parametric curve is dy dx, just like the slope of any curve. But to get the change in y compared to the change in x, generally x and y are separated. We already have the derivatives of x and y with respect to time. And so the way we do it is we do dy dt over dx dt. It should make sense that dy dt is the one on top because we want dy on the top. It's kind of like the dt's cancel each other out. I mean, I wouldn't write that in my work, but so kind of algebraically, it looks like it makes sense. So if we're going to do it at time, okay, now if we write that down, we get 3 sine t squared over cosine t cubed. I got to write small because I didn't give you guys much room here. But instead, it's only one sheet of paper. That's nice. You need time. Like, oh, but they gave us x and y. So what's the time? Do you recognize this xy pair? Oh, there it is. Oh, that's at time 2. So they didn't straight out say it, but we're looking for dy dx at time 2. So that's going to be 3 sine of 4 over cosine of 8. Now, I know I entered those equations in my calculator, but I'm going to go and just type this straight in. 3 sine 4 divided by cosine 8. I could write a decimal for it, 15.604. So the equation of the tangent line with point slope form may be y minus 5 equals 15.604 times x minus 4, and you're done. Just leave it. We're not being asked to do anything else with it, so I don't see any benefit to trying to get it in like slope intercept form. Find equation tangent line. Classic question in Calc AB also. The only thing is you had to realize that dy dx, slope of a parametric curve, is dy dt over dx dt. I think you guys can remember that. Find the speed of the object, not velocity, speed. Now, speed is the absolute value of velocity, the magnitude of the velocity without direction. And it's this idea, we can write it up here if you want, that you have this, parametric curve, and at any point it has an x velocity and it has a y velocity. So it's like we have a velocity vector, and you have a x component and a y component. And that's what these are. This is velocity in the x direction. This is velocity in the y direction. Derivative of position with respect to times velocity. So we want the overall velocity. Well, that's going to be the length of that line, which is the hypotenuse of a right triangle. So we're going to use Pythagorean theorem. It's the square root of vx squared plus vy squared. Positive. That's how you find speed with two-dimensional motion. Okay, so for us, or you could write it as dx dt squared plus dy dt squared. These aren't second derivatives. It's the first derivative squared. So for us, that is the square root of cosine. Now this is at time 2. So that's cosine of 8 squared plus 3 sine 4 squared, including the 3 gets squared. And we can just put that in our calculator. So we do square root, parentheses cosine 8, close, squared, plus parentheses 3 sine 4, close, squared, close. 2.275 rounded truncated comes out to the same through decimal accuracy from your calculator. There you go. There's your speed. All right. C. So, so far, I don't know. I thought parametrics weren't that bad. They're a lot like regular 1D motion. Find total distance. Now, total distance comes from a similar idea as this right here. Now, total distance last year with 1D motion was the integral of speed. It was the integral of the absolute value of velocity, right? Well, for us, speed now is that expression we wrote over here. It's the square root of dx dt squared plus dy dt squared dt. We're integrating with respect to time. We're going from 0 to 1. And so I'm going to use my calculator. This is where those equations will come in. Now, we don't plug 0, 1 into these. The square root doesn't undo the squares because you can't break up square roots like that. So on my home screen, I'm going to do math 9. That's it. Integration, square root, vars, y vars, function, y1 squared, plus vars, y vars, function, y2 squared, close parentheses, comma x, comma 0, comma 1. We're putting x's even though there's t's. And we get 1.458 rounded or truncated is the same through decimal accuracy. D, find the position. Now, the position is you're trying to find the xy coordinates. Okay, there's two different coordinates. Now, at time 3, usually what we do, and we did this a lot last year with 1D motion, is they would give us some known position and then give us the velocity or the derivative. And you could try and integrate each of these to get values or equations for x at any time, equations for y at any time. But look at those. You can't integrate those. You can't find those antiderivatives. So we want to really rely on our calculator to do definite integrals of those, because our calculator can integrate any of these. And the way we're going to do that is Fundamental Theorem of Calculus Part 1, FTC Part 1, that says if you integrate, Vx dt or dx dt, you're going to get x. And if you do it from a certain point, now we know the position at time 2 and we want the position at time 3. So we're going to say 2 to 3, and you're going to get x x3 minus x2. So I don't necessarily show all this work, but that's fundamental theorem of calculus. So if you integrate a derivative, you get the original function, and then you plug limits in. So that's what you're going to use to find x3. You know that x2 is 4, right? Because at time equals 2, x equals 4, and y equals 5. That was the initial condition they gave you. So we're going to say, all right, let's rewrite this. x3 equals 4 plus the integral of 2 to 3 of dx dt. Now I'm writing it in the way, instead of writing vx, I'm going to write dx dt because that's the way they labeled it. If they wrote vx up here, I put vx. So you kind of want your setup to match, use the, unless you really, you could also write cosine t cubed in here if you want. But 4 plus math 9 bars, y bars, function y1, comma x, comma 2, comma 3. This should be our answer. 3.953 truncated, 3.954 if you choose to round. That's 1/2 of your position, so you need the other half. This is x3. We're going to write these answers together, by the way. Anytime you find velocity, acceleration, position with parametrics, 2D motion, we write them sort of as a vector pair. So now if you integrate vy dt or dy dt, you're going to get y. Fundamental theorem of calculus part 1. We're going to integrate from the known time to the time we want. And so we're going to get y3 minus y2. And so this is what we want. So we're going to say, all right, well, y3 equals, and y2 is 5. We're going to add that to the other side, 5 plus the integral of 2 to 3 of dy dt. That's your setup. Show this setup, please. All right, now put that in our calculator. We're going to say 5 plus math 9, bars, y bars, function y2, comma x, comma 2, comma 3. And we're taking advantage of having entered those equations into the y menu. I think that's saving us a little time here. 4.906. So that's y3. Now we really would like to write these. Usually we're going to write these as an ordered pair. So you would say 3.953 comma 4.906 is the position at time 3. Okay. So that was a quick little review of parametrics. There's some other stuff that wasn't covered in there. The second derivative, the concavity of parametric curve, is gross. I don't know if you guys remember that one. You might take a look at that one. Also, on the back of your guys' formula sheet are a bunch of BC formulas, whereas AB doesn't have, their formula sheet doesn't have those. All right, let's try the next one. The next one is, let's see. Next one says, let f be a function, f4 equals 1. So it sounds like some initial condition such that all the points x, y of the graph satisfy the differential equation. Let g be function so that g4 equals 1. And then this is its differential equation. It's logistic. Oh, this is logistic. But this is also a differential equation. So if they give you logistic, it's often kind of tied into a logistic or into a differential equation kind of problem. So it might have some kind of like AB stuff on here. Logistic might be part of it. So it says, now the point breakdown here, the point breakdown in the last problem was 1, 1, 3, and 4. So part D was the most work. So it gives 4 points. The point breakdown here is, let's see, I guess I'm right, 5, 2, and 2. All right, 5, 2, and 2. So part A says, find y equals fx. Well, fx is this first differential equation, dy dx equals 2y 3 minus x. It's not logistic. It looks almost like this one. There would need to be a y there for it to be logistic, so don't be fooled. It's good to recognize logistic even if they don't tell you. That's logistic. Logistic is, let's see if we can remember this, k y m minus y, right? Where k is the growth rate and m is the carrying capacity. So this is logistic. And we're not going to be expected to probably solve a differential equation that's logistic. So we're just going to rely on all our knowledge. Now you can be like, I know nothing about logistic. I'm going to answer all these questions by just taking that equation and doing all the work I need to do on it. But it's a lot of work and you probably don't have time to. And it can be really fast if you just know the basics of logistic. Anyways, part A is not logistic. This is separating the variables. So I'm going to move the y to the left-hand side equals, I'm going to go and just distribute this to 6 minus 2x dx. That's a point. And this is the bulk of the points. This is 5 points. So this is just A-B stuff. Natural log of the absolute value of y equals 6x minus x squared plus c. Another point for finding the correct antiderivatives of both sides. Another point for writing plus c. Now we're going to find the c value. That's another point. So we were given an initial condition. They said that f4 equals 1. So that's your x and your y. So natural log of 1, and for y, 6 times 4 minus 4 squared plus c. Natural log of 1 is 0. So c equals, this is 24 minus 16 is 8 is negative 8. That's another point. You're going to plug it back into the original, into your equation, 6x minus x squared minus 8. And then you're going to solve for y. This last point is the most amount of work point, but also the least calculus. Exponentiate both sides. Get rid of the absolute value, plus or minus. And you should decide if it's plus or minus now. Use the initial condition. If I plug 4 in here, 24 minus 16 is 8, minus 8 is 0, e to 0 is 1. I need to get a 1 out, a positive 1, so we're going with the positive. And so y equals f of x equals e to the 6x minus x squared minus 8. Now, you should also remember that anytime you solve a differential equation, you have to give the domain. If you don't, you're losing this last point. So the domain is tied to two issues. The domain of this in general, are there any discontinuities, any places we need to break this up, any values of x that would cause imaginary, division by 0, so forth? Nope. Also, you need to worry about, so you got to look at that, but you also need to look at the original differential equation and say, are there any x or y values that will cause problems there, cause it not to be differentiable? Now, a curve can be continuous and have a domain even at a place that is not differentiable, like a corner or cusp, vertical tangent. But on the solutions of differential equations, we have to leave those out. We have to do a single open interval. No issues there, no issues here. So the domain is negative infinity to positive infinity. But you need to have that with your answer to get full credit. So part A was straightforward, solving differential equation, calc AB. Part B says, given that G4 equals 1, which they already told us, and just write down, find the limit as x approaches infinity of g of x. Now, this g of x is the logistic curve. Just to show you guys a sketch, it has a carrying capacity, horizontal asymptote, and then y equals 0. And it goes like that. It has an inflection point that's at half the carrying capacity, which it also has its greatest growth rate. So this is a rough graph of gx, right? And so we're saying, well, what's the limit as x goes in infinity? Well, it approaches the carrying capacity, which right here, dy dx, I'm just going to write right here, equals 2y 3 minus y. And we said that this is ky m minus y. And so the carrying capacity is 3. Done. There's another question, I think, though. Find the limit as x approaches infinity of g prime of x, which is the slope of the logistic curve. As x goes to infinity, what happens to the slope? It goes to 0. It's approaching a horizontal tangent. Done. There you go. Now, if you didn't know logistic, the way you could have answered these questions is by solving this differential equation, which is a ton of work, taking the limit of it correctly, taking the derivative of that ugly answer, and then taking the limit of that one correctly. I mean, it would be a whole page of work. It would take you 15 minutes just to do part B if you're going to do it. But if you know logistic, you're done. Quick, easy. C, for what value of y does the graph of G have an inflection point? Hey, we know what value of y, by the way, which makes it easy. What does y equal when G has an inflection point? Okay, well, that happens at half the carrying capacity when y equals half the carrying capacity, which is 3 halves. So that's the y coordinate. Finding the x coordinate is much more work. We usually set the y value to that, and we use the model, the logistic growth model, which I don't think you actually might have to even really use on the AP test, even though we've kind of memorized it. I don't know if you guys remember it's y equals, now I'm trying to remember, m over 1 minus a e to the negative mkt, I believe. Is it a minus or a plus here? This might be a plus. Anyways, that's the logistic growth model. I don't even think you'll need it on the AP test, but we're just using the really basic kind of facts about logistic growth. Now it says find the slope of the graph of G at the point of inflection. And they give you this really strong hint here, just in case. They're really trying to help you not make your life worse. Find the slope of the graph G. Like, oh, I got to get G prime. Well, that means I got to solve for G, or I got to write down the equation. Then I got to take derivative of that. Isn't G prime of X equal to dy dx that they gave you equals 2y 3 minus y? Yeah, you have it. And it involves y values, which might often normally be a challenge, but we know the y value. We just found it. So the slope of G when y equals 3 halves, you don't need to find the x. It's going to be 2 times 3 halves times 3 minus 3 halves. So that's going to be 3 times 3 halves, and so that's going to be 9 halves. So last part was worth 2 points. 1 point for the y value at the inflection point, 1 point for the slope at the inflection point. Part B was worth 2 points, 1 point for the limit of g of x, 1 point for the limit of g prime of x. And so there's an example of logistic. Now, differential equation problems might also be the place that they might give you Euler's method on free response, because logistic growth, or Euler's method used derivatives, differential equations, to write multiple tangent lines. So it's usually probably one or the other that they'll throw in as a part. But mainly, the most of the points on this problem are A-B kind of points. So little review of logistic and some other BC stuff. And then on the back, I give you polar function. Now, polar, I think this one, I thought polar was harder than parametrics. And usually on that AP test, they either give you a polar or they give you a parametric free response, one or the other, usually. The basic idea, just to show you real quick little review, is that if you have a point that has an xy pair coordinate, you could think of it as xy. Those are called rectangular coordinates. And that has to do with the x position and the y position. But another way to identify the location, and that's just to identify the location of a point. Another way to identify the location of that point is to draw a line from the origin to it and call that the radius, and then draw the angle from the positive x-axis. And by telling it how far, what angle you're at, and what the distance from the origin is, then that would give you the same point. Now, the relationships come from this. So you could write this out, and one relationship is that x squared plus y squared equals r squared. So that's one way you can find the radius. And so then r equals the square root of x squared plus y squared, just positive because it's a distance. Also from this, you can use basic trig and say, okay, well, if I want to find x from r and theta, which basic trig function uses this side and that side? This is the adjacent side to that angle, so that would be cosine of theta equals adjacent over hypotenuse. And from that, you get that x equals r cosine theta. We use that a lot. If you want to find y, you do sine theta equals opposite over hypotenuse. And from that, you get y equals r sine theta. So these are some of the basic relationships for polar. And we use them a lot, so you might get to a point where you start just to memorize the x equals r cosine theta, y equals r sine theta. Don't mix them up. They get used a ton. I'd write them down every time I needed to use them. But if you need to, you can rederive them pretty quickly, okay? And you know you're going to have questions on multiple choice and free response that have to do with this, so it's going to come up several times. The curve above is drawn in the xy plane and is described by the equation in polar coordinates. Now, polar coordinate equations usually are radius determined by theta instead of y determined by x. And the domain is angles, okay, where r is measured in meters. So, okay, they have actual length units in here. Theta is measured in radians, always radians. The derivative of r with respect to theta is given by this. So they gave us drd theta, which isn't, we could have done that. Derivative theta is 1. Derivative sine is going to be cosine 2 theta with an extra 2 in front because of chain rule. So they gave us that, but that would have been easy to figure out ourselves. Now, part A says find the area inside the polar curve. So just to remind you, the way that polar curves are graphed is you're starting here at theta equals 0, and then you're slowly, making your way along the curve to these separate points. And so you got to keep that in mind. And so this is theta equals 0, and then this over here is theta equals pi, and that's what they said, 0 to pi. So we're going to need to keep that in mind when we do the area. Those are going to be our limits. Now, the way we get the area of a polar curve, there's a formula that you should probably just memorize. I don't think I'm going to go through the derivation of it now, but I'll probably do it on some lesson in the future. But it's 1/2 r squared d theta. That's always the area in a polar curve. So let's see. So we could go ahead and just, write equals 1/2. The limits are 0 to pi. And the radius is theta plus sine 2 theta squared. Don't forget the squared, put parentheses. Now, this is a graphing calculator problem. Okay. So we're going to use our graphing calculator to do this. We could, no, I don't think we can integrate that by hand. Even if we could, we don't want to. Now, on our calculator, I would not put it into polar mode, even though it has a polar mode. We just really want to integrate this single variable integral. And so we're just going to plug x's in, just like when we integrate things with t's in Calc AB or whatever, we just put x's. If you want to integrate with respect to y, you just put x's. So now we might be using this equation multiple times. I don't know if it's going to be worth it to put it into the y menu just in case, so you don't have to retype it. That's up to you. So, you could if you want. So that's R. So from the home screen, I'm going to go Math 9, vars function y1 has my r function squared, comma x, comma 0, comma pi, and then also don't forget the 1/2. So we got to times it by 1/2. And that's our answer. It is 4.382 rounded truncated 3 decimal places. So I think this is a formula to memorize. I mean, I often tell you guys to not memorize a lot of things, but I think that one's worth it. I mean, I'll show you the derivation on an upcoming BC study group packet, but for now, we're just doing a quick review. B says, find the angle that corresponds to the point on the curve with the x-coordinate -2. Okay, now look at the picture. Where does the x-coordinate equal -2 would be right here. We're trying to find that point. We're actually trying to find the angle that gives you that point. Okay? You should expect to get an angle in the second quadrant between pi over 2 and pi. Right? This is pi over 2. If you don't get an answer between pi over 2 and pi, you probably did something wrong. Now, how do we find the angle when the x-coordinate is -2? Well, this is where the x and y equations come in. X equals r cosine theta, right? And r is the radius, so we can plug that in. Theta plus sine 2 theta, cosine theta. And if you want to know theta when it equals 2, then set it equal to 2 and solve the equation. Now, the way I would solve this on my calculator is I would move everything to one side equal to 0. And then I would graph that, but a really simple graph of that. So I'm going to put that in my Y menu. Now I have this other one on there. I'm just going to turn it off. And I'm going to put parentheses x plus sine 2x. You could get rid of the parentheses. Parentheses x plus sine 2x. You could distribute the cosine theta. Cosine x, close it, -2. And then I'm going to go to window. And I'm going to say, well, where do I expect this answer to be? It's good to restrict it. Well, we said it should be between pi over 2 and pi. There might be other solutions in other quadrants just algebraically, and you might be tempted to put them. Now, all I care about is the x-intercept of this. I don't need a beautiful version of this graph. This graph isn't going to make any sense to what I'm looking at up here. You should get one answer somewhere kind of in the middle. No. Okay, let's double check our work. What did I mess up? Pi over 2 pi. We're in radian mode. Let's just say 0 to pi for a second. It shouldn't be. So there's the graph. So something's up. It's not crossing the x-axis. So I don't know if I typed it in wrong. Y. It's supposed to be x equals r cosine theta, right? Okay. We have theta plus 2 sine theta, cosine theta. Oh, shoot. It's supposed to equal -2, which makes that a plus. That should be a plus. I'm going to go back to my window of pi over 2 to pi, graph it. That's why it's good to know where your answer is supposed to show up too, because then if they don't show up, maybe you'll find your mistake. So there it is. We want to find the x value of that. So I can calculate 0. This is pi, so this is like 2 to 3. So you can say maybe like 2.5 to 3, guess 2.8 or something. Just quick. So theta, but write theta. Theta equals 2.786. 3 decimal accuracy, rounded truncated comes out the same. And that's your answer. The point breakdown on this question is 3, 2, 2, 2. So part A was 3 points. It was 1 point for what was inside. It was 1 point for the limits and the constant. It was 1 point for the final answer. People love to forget the 1/2 on that formula. That was 3 points. This is 2 points. 1 point for setting up this equation that eventually we solved, and 1 point for the answer. C says for theta from pi over 3 to 2 pi over 3, dr d theta is negative. They're telling you that dr d theta is negative. What does this fact say about r? What does this fact say about the curve? Dr d theta is the derivative of the radius as theta changes. The radius, if it's negative, means the radius is getting smaller as theta gets bigger. Now look at the picture. It says from pi over 3, which would be like right around here, to 2 pi over 3, which would be like right around here. It says that the radius is getting smaller, and it kind of looks like it's getting smaller, right? It looks kind of like this was the biggest radius at that moment, and now it's getting smaller and smaller and smaller, closer to this, and then it starts to get bigger again. So it makes sense from the picture what they've described. Now we could have probably figured out where it was negative if they asked us to, but because we have dr theta, we could have solved that inequality, trig inequality, on our calculator. But they're just telling us where it is. Negative. What does it say about r? It says that r is decreasing. So dr d theta negative means that the radius is decreasing on pi over 3 to 2 pi over 3. It might be good to mention where this is at. What does it say about the curve? Well, the curve isn't decreasing. The curve is getting closer to the origin. That's probably the what we should say. And I think it might say to justify, it could say justify your answer or explain your reasoning. So I'm going to write this answer like they were really asking me to really support my answer. The curve is getting closer to the origin, which we also, I don't know if you guys remember, we call it the pole for polar coordinates. The origin, since two things. Since the radius is decreasing, but here's the problem. If the radius is negative and it's decreasing, then it actually means it's getting further from the origin. So the fact that the radius is positive and it's decreasing means it's getting closer to 0. Since the radius is decreasing and the radius is positive for all those values, so it's not just dr d theta is negative means it's getting close to origin, because if the radius was negative at the same time, actually getting further from the origin. If you had a negative radius and a positive dr d theta, it'd be getting closer to the origin. So getting closer or further from the origin is kind of a lot of times what they are looking for if you're talking about an object on the curve. And sometimes they combine parametrics and polar together. D, find the value of theta on the interval 0 to pi over 2 that corresponds to the point on the curve in the first quadrant. First quadrant, we're trying to find theta for a point with the greatest distance from the origin. Justify your answer. Greatest distance. Absolute maximum distance is what we're looking for here. We're looking for max distance from the origin, which equals max absolute value of r. It's not max r, because it could be the min r. If there's a negative r that's bigger magnitude than the biggest positive r, then that's further from, that's distance is always positive. On 0 to pi over 2. They did say first quadrant, but they also said 0 to pi over 2, which is the first quadrant. Those are going to be your endpoints. And so we need to do EVT. So we have endpoints. We need critical points. And so critical points are going to happen when we find the derivative of r. So r prime is dr d theta, which they gave us. And even if they didn't, we could have figured it out pretty easily. And we want to set it equal to 0 or undefined. That's how we find critical points. This is all stuff you need to write. You need to write dr d theta. You don't need to have the r prime. Dr d theta. And you got to have the equals 0 undefined. Okay. And we're going to use our calculator to solve this. You can kind of see where the radius kind of hits like a big point right here. Kind of looks like a potential answer, but the endpoint looks further. I mean, from this picture, this looks like the answer if we were going 0 to pi. That'd be first and second quadrants. In the first quadrant, that is going to be the answer, I think. That looks like it's the furthest. So we kind of have an idea of where it's going to happen. It's probably going to be at that critical point. That doesn't mean we can leave that out of our analysis. You can't be like, look at the picture. That's my justification. So we're going to just delete. I'm going to put the derivative in here and solve it. I mean, you could solve this by hand if you want. I mean, you have a calculator. I mean, this is basic trig. It's actually not too bad. You say, okay, well, what's alpha? When does cosine equal -1/2? Or just positive 1/2 at first. Cosine curve looks like this. It's 1 root 3 over 2 root 2 over 2 1/2, pi over 6, pi over 4, pi over 3. It's pi over 3 is the reference angle. Quadrants 2 and 3 is where it's negative. So then you could write 2 theta equals now. Just make sure I did all that right. That doesn't. Okay. Okay. I was thinking, our answer is it's supposed to be in quadrant 1. This is 2 and 3. Well, it's going to work out because 2 theta equals quadrant 2 would be 2 pi over 3 plus 2 pi k. And quadrant 3 would be 2 theta equals 4 pi over 3 plus 2 pi k. And so then you got to divide by 2. And you get theta equals pi over 3 plus pi k. And theta equals 2 pi over 3 plus pi k. We only want values that are between 0 and pi over 2, which is that one. So theta equals pi over 3 is your critical point. Or you could have done it on a calculator, which I'll show you right now, and you might be like, yeah, that's quicker and easier, and I probably make less mistakes. Let's just put this equation in our calculator, go to the window and say 0 to pi over 2, first quadrant, and just look for the x-intercepts of this graph. And there should be 1. And there it is. I'm going to do second calculate 0. It looks like it's just, between, 0.9 and 1.2 and guess like 1. So instead, you could have just said, theta equals 1.047197. Now I'm carrying extra decimal points because I need to use this in future calculations. Let's see, what's pi over 3? Oh, it's the same, 1.047197. Okay. I personally would have done it that way. This is all, don't force yourself to do extra work if you have a calculator. It saves you tons of time and mistakes. Okay. So we have our critical points. We have our endpoints. We're going to make a table to just organize our information. We're plugging values of theta into R. The equation for R is theta plus sine 2 theta. I like to write this on here to make sure I don't plug things in the wrong spots. The endpoints are 0. The critical point is 1.047197, because if I did on my calculator, I wouldn't necessarily realize that was pi over 3. So we'll just put the decimal, and then the other endpoint was pi over 2. And I have this equation, I think, in my Y menu, right? Nope, that's the wrong one. I had it before, but the quick way of doing this is you could put it into your Y menu and then go to table, and you might have some other values there from last time you used it. And so you could put 0, 1.047197, and pi over 2. And then it gives you the values, and you can write these down. So this is 0, which makes sense from the picture, right? Doesn't the radius look like it's 0 at theta equals 0, right? And then 1.913222, and then 1.570796. And so there's our max. We're looking for the max. Also, actually, we're doing absolute value of R. So it would be the absolute values of these things. But the radius is never negative. So, but it might be good to show that in your work, that you know you're looking for the absolute value. So we're going to write the answer nice. We're going to say the, let's see, the point, let's see, the greatest distance from the origin is 1.913. And I think they have units here, right? Didn't they say feet somewhere? Thought I remember seeing feet. Yeah, R is measured in meters. Oops. Is 1.913 meters at theta equals 1.047 radians. Okay, so that's just the answer. By extreme value theorem, do not abbreviate it. Extreme value theorem, write it out. You got to name it. It's not enough to name it, though. You got to explain how it works by checking endpoints and critical points. There you go. Nice thorough answer. Okay. I guess on the other problems, the area, I guess we could have wrote was meters squared. I don't know if they would have taken off points for that. And I mean, BU is an angle, that's radians. Usually you don't have to write radians with angles. It's assumed that if you don't put units on an angle, it's radians, but I don't know. If they say anything about putting units in this angle, I'd put the radians on it. So that was a good quick review of Puller. So crash course today. This is crash course. Covered most of the BC stuff other than recently series, which we've been doing those already. So you've seen it all. Quickly, we're going to take a practice test. You're going to see how you do. You're going to have a formula sheet, so it's going to make it a little easier. You don't have to memorize all these things, but you should be trying to, as much as possible, not rely on that formula sheet when you're getting ready, when you're doing assignments, because you need to learn those. So, all right.